Asteroid impacts have always been a fascinating concept, although uncommon. Even today, we see news articles of asteroids reaching the surface of Earth, and they make for interesting subjects of disaster movies. Why? Well, they are likely to have caused the mass extinction, which wiped out 76% of all species on the planet 66 million years ago. Was this a one-off, or could such an event happen again? And if a large asteroid was on course to strike Earth, could we prevent it and survive using current technology? I'm Alex McCohen, and you're watching Astrom. Join me today as we learn about the DART mission, humanity's first attempt to change the course of an asteroid to protect our world from future planet-ending threats. Major impact events have significantly shaped Earth's history. Going back to the very early solar system, one of the biggest impacts in our history may have formed the Moon, where a planet-sized object named Theia collided with young Earth. As time progressed, we may now have oceans full of water thanks to collisions with asteroids, and since then, asteroids have also potentially caused several mass extinctions. One of the most well-known impact events left the Chicxulub crater, which is believed to have caused the extinction of dinosaurs 66 million years ago. There is an inverse relationship between the size of an object and the frequency of such events. Small objects frequently collide with Earth, while large object collision events are very rare. And as the solar system ages, large asteroid impacts become less common. You see, when asteroids collide with something, they either fragment into smaller chunks or they get integrated into the larger bodies like the planets. It is estimated that Earth gains 15,000 tons per year this way from meteors entering its atmosphere. Impacts actually happen all the time on Earth, a lot more than you may think, but most are barely noticeable. Meteors or shooting stars are tiny objects with sizes ranging from sand grains to stones only a few centimeters across. These burn up as they enter Earth's atmosphere. So, how many do you think hit Earth's atmosphere on a daily basis? The figure may surprise you. 25 million. And guess what the biggest meteor is likely to be on any given day? 40 centimeters across. The biggest one on a yearly basis is around 40 meters, and every century we get one that is at least 20 meters across. The objects that manage to survive the Earth's atmosphere and land on the surface are called meteorites. These have to be somewhat larger than normal shooting stars to survive, and most of the time what's left of the object upon reaching Earth's surface is about the size of a brick. These objects cause large trails in the sky with spectacular colors known as fireballs. Every 2,000 years or so, a meteor about 100 meters across hits Earth, blasting through the atmosphere, causing significant damage to the area from the impact itself, but also from the airburst associated with it. And then you have objects large enough to threaten civilizations on Earth, objects over 10 kilometers that only come around once every several million years or so. The chances of anyone alive today encountering such an event are very close to zero. One of the good things about larger objects is that they are also easier to spot, and scientists think they know of all nearby asteroids above the size of 10 kilometers with a very high degree of certainty. But smaller, less easy to spot meteors are still a big threat on a more local scale. About 1,500 people were injured in 2013 when the Chelyabinsk meteor exploded over Chelyabinsk in Russia. Around 7,200 buildings across 6 cities were damaged by the explosion shockwave. Luckily, no one was fatally injured during this incident, but imagine if such a disaster were to happen in a highly populated region. Needless to say, the results would be catastrophic. This is why it is very important for us to be able to detect and prevent this before it has a chance of happening. One of the ways to do that is for us to find and track objects in space that might be a threat, and we are doing this faster and more efficiently than ever before. We've discovered over 20,000 new potentially dangerous asteroids in just the past 2 decades, with about 30 new discoveries added each week. Most of them have harmless orbits. But what would we do if we ever found an asteroid that was on a collision course with Earth? This was what NASA was trying to find a solution for with its DART mission, or the Double Asteroid Redirection Test. DART was a joint project between NASA and Johns Hopkins Applied Physics Laboratory, with international partners in Italy, Japan, and the European Space Agency. Its goal to try to redirect an asteroid's path by colliding a spacecraft with it. Before DART came along, many different ideas were floated about the best way to prevent an asteroid collision. If we had enough warning and if the asteroid was small enough, we could send a spacecraft to ride along with an asteroid to act as a gravity tractor. Over time, the presence of the spacecraft could gravitationally influence the asteroid just enough to redirect its orbit slightly out of the path of Earth. It sounds a little far-fetched, but in 2015, NASA published an article on their webpage stating that this was a workable solution. Perhaps a more well-known idea is that of just sending in a nuke. Asteroids aren't very densely packed, so exploding them into tiny pieces ought to be easy enough to do. But although this idea was popularized by films like Armageddon, it might not actually work as well in practice, as the momentum of the asteroid would be largely maintained even as its form shattered into pieces. If the resultant pieces were big enough, this would have the unfortunate effect of turning a metaphorical bullet heading towards Earth into an equally deadly shotgun spray. A third idea was about sending reflective mirrors to an asteroid. It's a well-documented fact that as comets pass by the sun and heat up, they frequently start out gassing, giving them added propulsion away from the sun. Spacecrafts with mirrors that traveled to an asteroid and reflected sunlight onto its surface at the right location could attempt to cause similar outgassing, letting the asteroid itself propel itself out of the path of Earth with its own released gases. But the creators of DART settled on perhaps the simplest solution, and one that we had successfully pulled off before with a comet to directly impact the asteroid. Not to blow it up, but to hit it just hard enough to knock it off course. The kinetic plan was settled on, but mission planners needed to greenlight a suitable test asteroid to hit, and so scientists settled on Dorphos. This asteroid was first discovered fairly recently in 2003. It is the small moon in a binary system orbiting around the larger Didymos, which was spotted in 1996 by the Spacewatch project in Arizona. Dimorphos is only 160 mm across, which is much smaller than the 780 mm Didymos, and has an orbital period of 11.9 hours, and maintains a distance of around 1 km from its larger neighbor. The system orbits the Sun every 2.1 Earth years, and made its approach to Earth in October 2022, coming within 10.6 million km, the closest it's been since 2003, meaning this was the perfect time to visit it. It was this closeness that caused NASA to choose Dorphos as their target. It was relatively easy to get to. But crucially, it was not so close as to be on a collision course with Earth. Scientists were confident that even once knocked off course, the Earth itself would not be in any danger. With their target set, NASA needed to build the perfect spacecraft to perform the deflection. Compared to other spacecraft, DART doesn't have a lot of frills. It's about the size of a refrigerator and weighs just 610 kilo, which is minuscule compared to Dorphos's estimated weight of 5 billion kg. DART has one payload, an aperture camera called Draco, short for Didymos Reconnaissance, an asteroid camera for optical navigation, as well as sensors and an autonomous navigation system. It also comes paired with a small secondary spacecraft called Lea Cube, making it a binary spacecraft visiting a binary system built by the Italian space agency ASI. Lea Cube is a small cube set with his own autonomous navigation system designed to separate from DART 15 days before impact. Lea Cube is tasked with recording the impact and his aftermath with two optical cameras named Luke and Leia. Yes, you heard that correctly, Star Wars fans. The Lea Cube weighs just 14 kilo and is only about 30 centimeters long. It would fly by the asteroid system using its own autonomous navigation system. The DART spacecraft was also designed to be running autonomously. Due to the latency between sending and receiving instructions caused by the distances between Earth and the spacecraft, DART needed to locate the moonlet, detect a perfect spot for the impact to happen, and then aim itself appropriately. This is where DART's smart nav came in handy. This autonomous optical navigation system could identify and distinguish between the two bodies and detect the target and then direct the spacecraft towards it. And surprisingly, all this would happen within only an hour before the impact. After blasting off on the 23rd of November 2021 on a SpaceX Falcon 9 rocket, DART spent the next 10 months in transit. In the 4 hours leading up to the impact, at a distance of 90,000 kilometers, DART's internal navigation system took over, and 90 minutes before impact, its smart nav system put the spacecraft on its final trajectory. When DART was 24,000 kilometers away, Dorphos became visible on camera, taking up 1.4 pixels. This is one of Draco's last images where you can see both Dorphos and his parent asteroid in the same frame. As DART hurtled closer to its target at a speed of 22,000 km/h, Dimorphos and its potential impact site came into spectacular view. In this image, taken just 3 seconds before impact, you can really see how Dorphos is a loose pile of rubble, essentially left over from the solar system's birth. This remarkable photograph is DART's final fully transmitted image. It was taken at a distance of 12 kilometers, a mere 2 seconds before impact. For reference, the scale is roughly 3 centimeters per pixel, and here finally is DART's last partially transmitted image. The downlink was interrupted by DART's previously scheduled, shall we say, disassembly. As strange as it sounds, this is my favorite of these images. Its incompleteness seems to capture the drama and intensity of the moment, as though freezing for all time the breathtaking instant when DART completed its 17.5 million kilometer journey in the blink of an eye. To the very end, DART did what it was designed to do with incredible precision, and it's a testament to the ingenuity of those at NASA. Here is the entire sequence sped up and played as a time-lapse. The video you see corresponds to the final 5.5 minutes of DART's final trajectory. As you'll notice, some of the images look a bit blurred. That's because DART's ion thrusters came into play, causing vibrations to the spacecraft and its camera. This sequence is incredible to me due to the speed involved. It hits such a tiny object, and I'm astonished some of these images are in focus at all. Imagine how quickly the camera had to adjust to the rapidly approaching object. Now, I'm sure you're itching to know whether the impact was successful. To relieve you of the suspense, the answer is yes. In fact, the early results have surpassed expectations. Before DART's kinetic impact, NASA defined success as a change in Dorphos's orbital period of at least 73 seconds, yet based on what we know so far, the data shows that DART shortened Diorphos's orbit by a full 32 minutes, from 11 hours and 55 minutes to 11 hours and 23 minutes, even with a margin of error of plus or minus 2 minutes. That is 25 times NASA's benchmark. A truly remarkable outcome. The impact released 19 gigjoule of energy, the equivalent of 5 tons of TNT, and blasted a crater up to 150 meters wide in the asteroid surface. Pretty big considering the moon was only 160 meters to begin with. It was also enough to change the shape of Dorphos's orbit and the asteroid itself. Dimorphos's orbit was originally very circular around Edmus, but after DART hit, this path became more elongated. The orbital time also continued to drift over the next few weeks before settling on 11 hours 22 minutes and 3 seconds. As for the shape, before the impact, Dimorphos had what is known as an oblate spheroid shape, a bit like a slightly squashed ball. Afterwards, it had become a triacal ellipsoid, similar to an oblong watermelon. It's fascinating to consider the forces that must have been at play for this change of shape to occur. And it also highlights the fluffy nature of asteroids like Dimorphos being so loosely tied together by gravity. It increases the capacity for shape changes like these to happen if hit with the right impact. Not to worry though, even with large margins of variability, scientists know that even with this collision, the orbit of Didymos won't change enough to ever cross paths with Earth. But if there was an Earth-bound asteroid, this little nudge early enough in advance can impact its orbit enough to take it off a collision course. But why did the impact shorten Dorphos's orbit? Well, due to orbital mechanics, the crash pushed Dimorphos closer to Didymos, which in turn sped up its orbit. Scientists confirmed this finding through observations from optical telescopes here on Earth, including the Southern Astrophysical Research Telescope in Chile. SAW also happened to capture some of the very best images of the encounter, including this breathtaking photograph of a 10,000-kilometer trail of debris 2 days after the impact, making it look like a comet. Because Didymos is a two-asteroid system, its brightness fluctuates as Dorphos passes through the shadow of its parent asteroid and out again in front. By tracking the light curve, scientists can calculate the speed of Dorphos's orbit. These results were further supported by radar data collected by observatories in California and West Virginia. DART and Earthbound telescopes weren't the only cameras watching the event though. The closest images of the crash scene were captured by Lea Cube, and they are phenomenal. As I previously mentioned, Lea Cube separated from DART 2 weeks before impact to conduct its own flyby using autonomous navigation systems. 2 minutes and 45 seconds after DART's impact, Lea Cube flew past Dimorphos to photograph the impact site with its evolving plumes and ejector. Here is an action-packed image of Dimorphos after the event with Didymos overexposed in the foreground. Notice the huge plumes of material emanating from Dimorphos. Some of them seem to be spiraling almost like tendrils of a vine. This indicates that the material changed directions as the plume grew. We think this phenomenon may be caused by the composition of the asteroid, as impact tests on finer sediment mixed with coarser debris sometimes yield similar ejection patterns. This is a more distant image also captured by Lucia Cube, with Dorfus on the rightmost side. Notice how the asteroid itself is barely visible due to the huge clouds of material splashed up by the impact. Hubble and the Webb telescope also got in on the action of imaging the aftermath of DART's impact. Here you can see a spectacular series of images from Hubble showing the progression of the plumes in size and number. Notice how some of the plumes look like rays emanating from the asteroid. Strangely, some of these rays appear curved. Why? As of now, NASA isn't sure. While Hubble has observed the impact from the visible spectrum of light, the Webb telescope captured its own images from the infrared spectrum. This is pretty impressive since Dorfus was traveling 3 times faster than Webb was meant to be able to track. The time-lapse you are looking at starts right before impact and continues until 5 hours afterwards. Notice the sudden flare of light coinciding with the material released from impact. I also love how the Webb images give you a great sense of the spiraling plumes emanating from the asteroid. Over the coming weeks and months, scientists will continue to study the data from DART's impact, but the real investigative work will be carried out in the future by Hera. Hera is a follow-up mission currently being carried out by the European Space Agency that launched on the 7th of October 2024, and will reach the Dilema system by 2026. Carrying a sophisticated payload of instruments including cameras, a spectrometer, and altimeter. Once it arrives, Hera will intricately document the size, shape, and composition of the crater left behind by DART's impact. Most exciting of all, Hera will conduct observations of Dorfus's internal and subsurface structures. This model will not only advance our understanding of the binary DIY system itself, but provide a more nuanced understanding of how NEO's physical characteristics influence the transfer of momentum, as well as how kinetic energy transfers to an NEO and ejected materials. All of this will allow for a greater understanding of DART's kinetic impact and provide a useful guideline for improving deflection technologies in the future. So, combine that with NASA's missions like NEO Surveyor, which aims to discover at least 90% of asteroids, 140 kilometers in size or larger, and it feels like humanity, for the first time, has actively reduced its chances of being hit by the kind of world-ending impact that likely wiped out the dinosaurs. NASA already keeps track of most near-Earth objects, but some asteroids like dark comets are harder to see if they don't reflect much visible light. NEO Surveyor is proposed to launch in 2028 and will scan the solar system for such objects by taking infrared readings, detecting hard-to-spot asteroids by seeing the heat they radiate when they are warmed by the sun. It will also be able to spot asteroids that approach Earth from our blind spots, such as ones coming directly from the direction of the sun, which ground-based telescopes might miss due to the glare. With even the hardest-to-see NEOs being detected, the technology proven by DART will be a shield that can keep our world safe. So, there we have it. Everything you could want to know about the DART mission. Right now, we've barely scratched the surface of deflection technologies, but if you look at what this mission has accomplished, it appears the future of planetary defense has taken a bold and promising first step. So, do you think this mission was worthwhile? Do you think we'll have to use this technology within our lifetimes? Let me know in the comments. If you've ever looked up at the night sky and watched a comet streak by, you will know of the wonder of watching one of these celestial visitors. Often seen with awe or fear throughout humanity's history, these bright-tailed objects in our skies were known as harbingers of change, and yet, in the last 50 years the tables turned on these icy wanderers, and it went from them coming to visit us to us being able to visit them. Scientists had long wondered about the nature and origin of comets. Where had they come from? How were they formed? In 1986, the first probe was launched to image Hall's Comet, and scientists began to find answers. But to truly understand comets, it would take more than photographs. A more physical approach would be needed. Between 1999 and 2005, 2 probes were launched. Their mission was to interact with comets in ways that had never been attempted before. One would bring collection equipment that would allow it to scoop stardust right from the comet's icy tail to help scientists analyze the chemical makeup of these frosty harbingers. The second would take a more forceful approach. Rather than quietly collecting a smattering of space dust, the second probe would crash headfirst into the surface of the comet itself, exploding with the force of 5 tons of TNT, to see what could be learned from the resulting crater and debris. And yet, although these two missions were two different comets, through chance, there was one comet that unexpectedly brought them both together. Tempel 1. I'm Alex McCone, and you're watching Astrom. Join with me today in today's Supercut as we explore the explosive story of Tempel 1 and how the Stardust and Deep Impact probes both were needed to help discover what lay at the heart of this space-worn nomad. In the early 90s, comets were still a bit of an enigma. By 1999, 8 different spacecraft had been launched to investigate comets in our solar system, with 5 of them having flown by Hall's Comet in 1986. But beyond that, only 2 other comets had been visited: Comet Giantini-Sinner in 1985 and Comet Grigg-Skeelup in 1992. And while some fascinating photos and dust samples had been taken as close as 200 kilometers from some of these incredible celestial bodies, comas and tails, comets still had many mysteries. What was their internal structure like? What were they made from? And how had they formed in the first place? In 1999, NASA scientists proposed the plan to hopefully answer some of these questions. It would be difficult to understand the internal structure of comets by simply looking at their surface. To know what was going on, scientists would need to dig a little deeper. Their plan was to create a crater in a comet using an impactor spacecraft which would collide with the comet at high speeds. As they would know the mass of the impactor and the speed it was traveling at, they could calculate from the size of the impact crater valuable information about the comet. Whether its surface was a loose aggregate of dust and ice, or whether it had a hard frozen shell. For instance, the comet they wanted to target was a short-period comet called Tempel 1, which had a nucleus of 8 km long and 5 km wide. Scientists weren't exactly certain what would happen when the impactor hit. Perhaps the impactor would punch straight through like hitting a snowdrift and not really create a crater at all. There were many theories, but scientists were eager to find out which was correct. NASA approved the project, giving it a budget of $330 million and named it Deep Impact. You might have thought that this was a reference to the 1998 Hollywood film of the same name, but apparently the names for both the project and the film had been come up with independently around the same time. Quite the remarkable coincidence. If so, as Deep Impact, the film, was about scientists trying to blow up a meteor that was on a collision course with the Earth by flying a spacecraft to it carrying nuclear warheads. There certainly seemed to be some similarities to the NASA mission, especially as NASA scientists worked on the film. I don't entirely buy NASA's claim of a coincidence, although fortunately for the Earth, there were some differences between the film and the mission too. Tempel 1's orbit was nowhere near the Earth's, and given the size of the impactor compared to the comet, there was no chance of knocking it off its current trajectory by more than a centimeter or so. It would be more like a fly hitting the front windscreen of a large vehicle. Additionally, nukes would not be necessary to create a crater on Tempel 1, or any kind of explosives for that matter. The sheer speed and kinetic force the impact would have when it collided with the comet's surface would be enough to create the crater, which some predicted would be roughly 100 meters across and 30 meters deep. With the mission going ahead, scientists began work on the Deep Impact spacecraft. The spacecraft was actually made with 2 parts, the payload and another larger mothership to carry it and record the result of the impact. The second section was called the Flyby. It weighed 601 kilos, was 3 meters long, and housed scientific devices, solar panels, a debris shield, and 2 powerful cameras, the high-resolution imager and the medium-resolution imager. These would take photos of the comet after the impact, as well as help with navigation. The impactor itself was smaller, only 372 kg, but it was still smart and housed the camera of its own. This camera, the impactor targeting sensor, would take photos of Tempel 1 right up until the moment of impact, streaming back the images it collected to its parent Flyby, which would then relay the images to Earth. There was considerable public interest in the mission, which NASA encouraged in 2003 by getting members of the public to submit their names to be recorded on a CD, which was placed on the impactor. Roughly 625,000 names were collected in this way to be carried directly to Tempel 1's surface. On top of that, NASA timed the impact to take place on the 4th of July, American Independence Day. While this may have been because it was one day before Tempel 1's perihelion and its proximity to the Sun may have produced clearer images, I suspect that the more likely reason for this date was that American scientists liked the idea of a large cosmic firework. Deep Impact launched on the 12th of January 2005 on a Delta Y rocket, but then a problem hit. Within a day of leaving the Earth's orbit, Deep Impact's onboard computers switched itself to safe mode, which it would only do if there was a fault. Something on board was apparently overheating. This gave scientists a bit of a scare, but fortunately, the cause of the problem was quickly found to be a minor programming issue. Acceptable heat tolerances had been set too low, so Deep Impact thought its thrusters were overheating when in reality, they were just fine. Engineers corrected the issue and Deep Impact was able to properly begin its mission. The spacecraft spent the next 6 months traveling to its rendezvous point with Tempel 1. In that time, it traveled 429 million kilometers. It had to course correct twice on the journey, but this was actually impressive as it had originally been planned for there to be 3 course corrections. One was just so precise that the other was deemed unnecessary. On the 25th of April, 2005, Deep Impact caught its first glimpse of Comet Tempel 1. Of course, NASA scientists couldn't manually guide Deep Impact as there was a several-minute signal lag. Deep Impact and Tempel 1 were now roughly 130 million kilometers away from Earth, more than twice the closest distance between Earth and Mars. Deep Impact's smart onboard programming would have to guide it in for the final leg of the journey. On the 29th of June, the impactor successfully released from the flyby and positioned itself into the comet's flight path to crash into it head-on. This was done for a few reasons. First, the front of the comet was in sunlight, which would allow for better pictures to be taken. Second, it would allow a greater accumulated speed to be reached, resulting in greater kinetic force. And on the 4th of July 2005, just 1 second out from the anticipated arrival time, the impactor hit. And what a magnificent spectacle it produced. Scientists were thrilled that they had struck so accurately. Deep Impact's payload had been traveling at 37,000 kmh and had struck with a force of 19 billion joules of kinetic energy. This produced the bright flash you see here, the energy of which is roughly equivalent to 5 tons of TNT. This flash was much brighter than scientists expected. It lit up the surface of Tempel 1. However, ironically, the success of the first part of the mission caused an unexpected negative side effect. A large dust cloud was kicked up by the impact, which obscured the flyby's view of the impact crater. Dust outgassed from the comet for the next 13 days, peaking 5 days in, which made it hard to see the results of this interstellar bullseye. Although, it did offer some interesting insights into the internal pressures going on inside the comet. Around 5 million kg of water and between 10 and 25 million kg of dust were ejected from Tempel 1 in that time. Fortunately, scientists were able to rely on other eyes, at least to capture images of the explosion. The collision had been observed through numerous other telescopes on or around Earth, including Hubble, Swift, and even many amateur astronomer telescopes. Still, this was a serious problem. Although this outgassing was fascinating to record, the primary purpose of the Deep Impact mission was to take photographs of the crater caused by Deep Impact. Without images of the result, many of the questions about Tempel 1 would remain unanswered, like about its structure and composition. Like a partially unwrapped gift, Tempel 1 had been opened, but it had not yet been seen what lay inside. Some other craft would be needed to complete Deep Impact's unfinished mission. Fortunately, another craft capable of doing so had already been launched and having completed its own previous mission, was now drifting serenely through space. It was about to receive another task. It's time to talk about Stardust. Let's go back to the late 1990s when cometary science was even more patchy. Although by this point we had sent 6 probes up to visit these enigmatic celestial bodies, not very much was known about their origins. It was believed at the time that comets were foreign visitors to our solar system older than the Sun, having been formed from the loose preolar grains of dust that orbit other stars before drifting the frarum, stoi ingselm, spoin betentestes, then towards us, only to be caught up in the Sun's gravitational pull. It was believed that this theory could be confirmed by traveling to one of these comets and picking up some of this loose dust or stardust that surrounds them in space. By examining the isotopic composition, scientists would be able to tell if it was unusual when compared to the dust given off by our own star. However, this was a challenging mission. As is often the case, it came down to a question of speed and energy. Comets travel through the inner solar system at speeds reaching 160,000 km each. While it was possible for a probe to try and match that speed, and come up alongside it. This had to be done without needing too much fuel, or the weight of the craft would be too heavy and thus too expensive to get into space in the first place. Initially, Stardust had nothing to do with Tempel 1. For this mission, scientists selected a comet known as V2. They believed that they would be able to get Stardust alongside VIL-2 at a relatively low velocity. However, this velocity would still be around 6.5 km/s or 23,400 km/h. As you can imagine, catching even particles at that speed would be extremely challenging. Although particles would likely not do too much damage to Stardust, being too small to really impact it, it would do irreparable damage to the particles themselves. When an object crashes at 23,400 km/h into a surface, the odds of it keeping its original shape and structure are incredibly small. Scientists would not learn much about the structure of these particles if they smash those particles into pieces. Not to mention the warping effect all that kinetic energy being suddenly converted into thermal would have on the molecular bonds involved. So what was their solution? What was their mechanism for catching objects traveling at those speeds? Well, much like how an airbag softens the blow for you if you're involved in a car crash, scientists realized that they would need an airbag of their own. Something that would not halt the particle all at once, but would reduce its speed over a longer distance, thus reducing the amount of crushing deceleration involved. For this, they found an incredible material that was basically air, solid air. They decided to use aerogel. Aerogel is a fascinating substance that was discovered in 1931 by Samuel Kistler when he made a bet with fellow scientist Charles Learned about jelly. As you've probably seen if you've ever made it yourself, jelly is formed of two parts. Firstly, a relatively solid structure.